Have you ever wondered what's really happening on the cold, tilted world of Uranus, the planet we've barely seen? Tonight, we'll travel across billions of kilometers to uncover its quiet storms, hidden moons, and invisible rings. No rush, no noise, just calm, clear science unfolding at the edge of sunlight. Let your curiosity slow down and your thoughts drift. Stay with us until the end. This is Calm Science Sleep. For a long time, Uranus seemed like the quiet one among the planets, distant, pale, and largely ignored. While Jupiter dazzled with its storms and Saturn with its shining rings, Uranus remained a soft turquoise sphere on the edge of sight. For decades, scientists thought they already knew enough about it, a frozen gas giant slowly turning in the dark. But in recent years, a quiet revolution has begun. New observations, computer models, and reanalyzed data have revealed that Uranus is far from dull. It is, in fact, one of the most intriguing and complex worlds in our solar system. It might help to remember that Uranus has always existed at the boundary of what we can see. Even its discovery was an accident. In 1781, the British astronomer William Herschel noticed a faint object that moved slightly against the background of the stars. He first thought it was a comet, but the motion didn't fit. Eventually, calculations confirmed it was a new planet, the first discovered with a telescope. That moment quietly expanded the known solar system for the very first time, doubling its size overnight. Beyond Saturn, another world was waiting, and with it came the realization that there might be many more. For the centuries that followed, Uranus remained a faint blue dot in the sky. Astronomers charted its orbit, calculated its mass, and learned that it was mostly made of hydrogen, helium, and a small but important amount of water, ammonia, and methane. Methane is what gives the planet its soft, milky blue color. Light from the sun enters the atmosphere, and methane absorbs the red wavelengths, reflecting only blue. It's a simple chemical effect, but the result is striking. Uranus glows like a distant piece of sky, turned upside down and frozen in place. Still, even after its discovery, Uranus seemed oddly quiet. Through most telescopes, it appeared as a small, featureless disk. No colorful bands like Jupiter, no broad rings like Saturn. Astronomers could only measure its brightness and temperature from afar, and there wasn't much to report. For a long time, Uranus was treated as a world without weather, without structure, without story. That perception changed slightly in 1986, when NASA's Voyager 2 flew past it. The encounter lasted only a few hours, yet it gave humanity its first, and so far, only close look at the planet. Voyager 2 revealed an atmosphere of hydrogen and helium, with traces of methane and perhaps deeper layers of exotic ices. It also discovered that Uranus is tipped on its side, with its rotation axis lying almost in the plane of its orbit. This means that the planet essentially rolls around the sun, spinning like a marble lying on its side. Its seasons are unlike anything on Earth. Each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. At the time, these facts seemed curious, but not dramatic. The photographs Voyager sent back looked strangely uniform. A flat, pale blue surface without visible storms or bands. Many assumed that Uranus was, in a way, the most boring planet in the solar system. Cold, quiet, uneventful. For decades, that reputation stuck. Funding agencies prioritized Mars, Jupiter, and Saturn. The last major mission to Uranus was the one that simply flew by, leaving behind more questions than answers. But the truth is, silence does not mean stillness. As telescopes became more powerful and computers more capable, Scientists began to revisit those old Voyager measurements with new tools. They compared them with modern infrared and radio observations from Earth-based telescopes. What they found began to rewrite the story. Uranus was not static at all. Beneath its calm exterior, it hides some of the fastest winds in the solar system, reaching speeds of nearly 900 kilometers per hour. It has a magnetic field tilted at an angle unlike any other planet, and its internal heat behaves in puzzling ways. Its faint rings, once thought to be rare, turned out to be more structured and dynamic than expected. Perhaps the most surprising discovery is how much Uranus still has to teach us about the formation of planets themselves. Its unusual tilt may be the result of a colossal collision billions of years ago. A world the size of Earth striking Uranus and knocking it onto its side. Such an impact could have reshaped the planet's interior, trapping heat deep below the clouds and altering the way its magnetic field flows. This idea connects Uranus to one of the most important questions in planetary science: how chaos and accident shape stability. Even in our orderly solar system, balance often hides the memory of great violence, softened over time, by distance, and by cold. Today, with new telescopes like the James Webb Space Telescope and the Atacama Large Millimeter Array, Uranus has re-emerged as a focus of attention. These observatories can see heat and light invisible to human eyes. They reveal faint temperature gradients, trace gases, and subtle shifts in brightness that change with the planet's long seasons. Scientists have begun to suspect that Uranus has a much more active atmosphere than previously thought, storms rising and fading slowly over the course of years, perhaps even decades. The seemingly featureless blue may only be the surface of a deep, dynamic system of winds, clouds, and ice dot, and then there are the moons, small, irregular worlds orbiting this pale giant. Some of them show hints of geological activity, fractures, and possibly even subsurface oceans. Their faint gravity shapes the delicate rings that encircle Uranus like an invisible crown. Each new observation adds a layer to a planet once considered simple, now revealed as beautifully complex. When we look at Uranus today, we are reminded of how much our perception depends on attention. For many years, it was simply too far, too faint, and too forgotten. Yet, with every new instrument, with every deeper look, it becomes clear that stillness can be misleading. What seems static may simply be slow, a rhythm stretched across vast distances and enormous spans of time. That is perhaps the quiet lesson Uranus offers. That silence in the cosmos does not mean emptiness. The faintest light in the telescope can still hold an ocean of unanswered questions. The slowest motion can conceal enormous forces at work. And the coldest world can still shape the story of how planets are born and evolve. In the calm blue of Uranus, there is a subtle reminder of patience, the idea that discovery often takes time, that curiosity must sometimes wait decades for clarity. Voyager's brief visit gave us only a snapshot, but even a single image can become a seed for generations of exploration. Each new analysis, each recalibration of data, reveals something unexpected. The planet once dismissed as featureless has turned into one of the most important subjects in the search for understanding how worlds change, age, and sustain hidden motion. Not so. When astronomers speak of returning to Uranus, not with a flyby, but with a long, dedicated mission, they are not just seeking to fill a gap in data. They are acknowledging that quiet worlds often hold the most profound secrets. Beneath the slow rotation, beneath the cold light of distant sunlight, Uranus is teaching us how little we truly know about the outer edges of our own home system. In a sense, this is where the journey begins. From the overlooked to the extraordinary, from the simple to the subtle, Uranus invites us to look again, and this time to keep looking. Because in its still blue glow lies the promise that even in silence, the universe continues to speak. After Voyager 2 passed Uranus in 1986, the planet slowly drifted out of public awareness. For a brief moment, it had been a triumph. Humanity's first encounter with a world almost 3 billion kilometers away. But the excitement faded quickly. No orbiters followed, no probes remained, and for more than 3 decades, Uranus circled in silence. Unvisited and nearly forgotten. A quiet world beyond our curiosity. The reasons were partly practical, partly psychological. Voyager 2's schedule was relentless. Jupiter in 1979, Saturn in 1981, Uranus in 1986, Neptune in 1989, 4 worlds, each observed for only a few days. Uranus received just 6 hours of detailed study before the spacecraft sped away forever. Lighting conditions were poor. When Voyager arrived, the planet's south pole was in full sunlight, while most of the north lay in darkness. Its cameras, limited by the technology of the time, saw only a pale disk with faint markings. To the human eye, it appeared calm, perhaps too calm, and soon it was labeled as dull dot in planetary science. Excitement drives attention. Mars offered hints of life. Jupiter and Saturn displayed storms and spectacular rings. Even Neptune's deep blue clouds captured imagination. Uranus seemed subdued, a softly glowing sphere with little visible drama. Once the headlines faded, the funding followed. While missions returned to Mars and Saturn again and again, Uranus remained untouched, the only major planet never revisited since its discovery. It became a blank page on the solar system's map, known, named, and rarely studied. Distance compounded the neglect. Even at its closest, Uranus lies more than 2.5 billion kilometers from Earth. A spacecraft would need more than a decade to reach it, far beyond the range of solar power. Only nuclear-powered systems can function there, and those are costly and rare. Each new proposal for an orbiter had to compete with nearer, cheaper goals. Without visible storms or clear prospects for life, Uranus was easy to postpone. Visibility also shapes fascination. Mars glows red to the naked eye. Jupiter and Saturn reveal detail through small telescopes. Uranus, faint and bluish, barely crosses the threshold of visibility. Few have ever seen it directly, and what cannot be seen easily slips from imagination. So it waited, far beyond the glow of public attention. Through the 1990s and 2000s, the lull deepened. With no fresh data, researchers re-examined Voyager's aging records, refining models but finding few surprises. Academic papers about Uranus dwindled. It was as if a book had been left half-read, the story known to exist but unopened. And yet, curiosity never fully vanished. Amateur astronomers kept photographing the distant planet, noting small changes in brightness. Ground-based observatories began detecting faint cloud patterns and temperature variations that Voyager had missed. Something, however subtle, was stirring behind that serene facade. The revival truly began in the 2010s. New instruments at the Keck Observatory in Hawaii and the Very Large Telescope in Chile captured Uranus in infrared light, revealing stacked cloud layers and deep-seated storms. The Hubble Space Telescope later observed bright white features, vast convective systems rising through the atmosphere. The once static planet showed movement and rhythm, following a seasonal cycle far slower than human attention. Uranus was not dead. It was simply slow, its weather unfolding on timescales of decades. This realization reignited scientific interest. Planetary researchers argued that Uranus and Neptune, the so-called ice giants, form a distinct class of planets, chemically and structurally different from gas giants or rocky worlds. Understanding them could clarify how most planetary systems in the galaxy evolve, since the majority of exoplanets discovered so far fall within their size range. In studying Uranus, we would be studying an entire category of worlds beyond our own, but turning that realization into action proved difficult. Throughout the 1990s and 2000s, NASA's focus moved elsewhere: Mars rovers, asteroid probes, lunar programs. Each decade's planning documents praised Uranus as high priority for future study, only for budget shifts to delay it again. The distance demanded patience. Uranus, in both orbit and history, taught that lesson well. Meanwhile, scientists extracted new information from what little data existed. Radio telescopes studying Uranus's magnetosphere found that its magnetic field tilts nearly 60 degrees from its rotational axis and is offset far from the planet's center. As Uranus spins, the field tumbles chaotically, forming a lopsided magnetic bubble. Computer simulations linked this to layered convection within the planet's mantle, an intricate interior quite unlike that of Jupiter or Saturn. It was another reminder that apparent simplicity often conceals deep complexity. Attention also returned to the moons. Reanalysis of Voyager's images showed that aerial titania and Miranda Bear fractures and landslides hinting at internal activity. Some models suggest they could host subsurface oceans warmed by residual heat or ammonia antifreeze, small, silent seas beneath their icy crusts. If confirmed, these worlds would join Europa and Enceladus as potential habitats for prebiotic chemistry, showing that even the outer darkness might shelter conditions for life by the 2020s. The forgotten frontier was no longer forgotten. In 2022, the U.S. National Academies of Sciences ranked a Uranus orbiter and probe as the top priority for planetary exploration in the coming decade. The concept envisions a spacecraft entering orbit for years, mapping the planet's atmosphere, magnetism, rings, and moons in unprecedented detail. Launched in the early 2030s, it could arrive by the mid-2040s, a fittingly long journey for a world that moves so slowly through its seasons. For the first time in generations, returning to Uranus feels within reach. The story of how Uranus slipped from curiosity is, ultimately, a story about attention, how it drifts, and how it returns. Our gaze follows brightness, motion, and promise. Uranus offered none of these at first glance, and so it faded from view. Yet science, like the planet itself, moves in cycles. What was overlooked can become essential again when new tools and new minds look outward. Curiosity, once quiet, begins to stir, and now it does. The forgotten frontier calls once more from the edge of sunlight, reminding us that exploration is not measured in urgency, but in persistence. To answer that call, we turn back to the lone visitor who first revealed this world, Voyager 2, the patient traveler that captured Uranus for the first and only time. In the next chapter, we will follow that journey. A brief, distant meeting between humankind and the cold blue planet that waited to be seen. When Voyager 2 approached Uranus in January 1986, it entered a realm of silence and distance that no human mission had reached before. After traveling for more than 8 years and 3 billion kilometers, the spacecraft arrived at a world that reflected sunlight as faint as starlight, pale, cold, and distant. For just a few days, humanity's gaze rested on Uranus, And then, as the spacecraft drifted onward, that window slowly closed. Voyager 2 was built for endurance. Launched in 1977, it used a rare planetary alignment that allowed gravity assists from one world to the next, a cosmic relay through the outer solar system. After photographing Jupiter's storms and Saturn's rings, the spacecraft continued toward Uranus, becoming the first probe ever to visit an ice giant. By the time it arrived, it had already traveled farther than any functioning spacecraft in history. As the encounter began, Uranus filled the cameras with a calm, uniform blue-green disk. To early observers, it appeared almost featureless. Unlike Jupiter's swirling bands or Saturn's golden rings, Uranus seemed quiet, a sphere without storms or movement. The pale images led many to assume that little was happening beneath the surface. Yet as the data streamed back, the calm appearance began to reveal its depth. Voyager found that Uranus is unlike any other planet. Its axis is tilted by nearly 98 degrees, causing it to spin on its side. For much of its orbit, one pole faces the sun for decades, while the other lies in unending night. During Voyager's flyby, the southern hemisphere basked in light, while the north was hidden in darkness. This peculiar geometry shaped every measurement: the winds, the clouds, even the faint rings discovered years earlier. It was as if the planet itself were turned sideways in both body and behavior. The probe's instruments recorded an atmosphere dominated by hydrogen, helium, and methane. Methane absorbs red light, leaving only blue and green to scatter outward, the reason for the planet's soft color. Beneath that calm hue, winds raced at over 700 kilometers per hour. Voyager detected subtle bands, faint clouds, and polar haze, details invisible to ground-based telescopes. It also measured temperatures as low as -224 degrees Celsius, making Uranus the coldest major planet in the solar system, even colder than Neptune. This frigid stillness puzzled scientists. Why did Uranus emit almost no internal heat compared with its twin? The answer, they suspected, might lie deep within its tilted interior. The spacecraft also revealed a magnetic field both off-center and tilted relative to the planet's axis. Unlike Earth's field, generated symmetrically around its core, Uranus's was displaced thousands of kilometers from the center and angled by nearly 60 degrees. As the planet rotated, the magnetic field swept through space in a complex, tumbling pattern, creating an irregular magnetosphere unlike anything seen before. This strange behavior hinted that Uranus's magnetic dynamo operates in thin, shifting layers rather than in a central molten core, a clue that its internal structure is more intricate than imagined. Voyager's instruments mapped the rings and moons as well. The rings, narrow and dark, reflected almost no sunlight, appearing only as thin arcs against the void. 11 were confirmed, each a few kilometers wide, confined by the gravity of tiny shepherd moons. Among the moons, 5 stood out: Miranda, Ariel, Umbriel, Titania, and Oberon. Each displayed unique geology, fractures, cliffs, and fault lines, evidence of ancient motion and internal heat. Miranda, in particular, astonished scientists with a patchwork surface of valleys and ridges, as if it had been torn apart and reassembled. It became clear that even in this distant cold, geological activity had once shaped these worlds. The spacecraft's radio instruments also measured the planet's magnetosphere and plasma environment, revealing how solar wind interacts with Uranus's sideways rotation. Particles trapped by the magnetic field formed bright auroras, dancing near the poles that faced away from the sun. But because of the planet's extreme tilt, Those auroras rotated in unpredictable ways, a chaotic ballet of magnetism and light. For all its accomplishments, the encounter was brief. Voyager 2 spent less than a day within close range and only 6 hours collecting its most detailed measurements. Then gravity carried it onward toward Neptune, leaving Uranus behind forever. The images and data, thousands of frames and readings, became humanity's entire direct record of the planet. No other mission has returned since. Yet that short visit transformed our view of the outer solar system. Voyager revealed that Uranus was not a static world, but a complex, layered system, a planet of ice, gas, and motion hidden beneath stillness. It showed that simplicity in appearance can mask extraordinary detail. And it reminded us that discovery often begins not with grandeur, but with quiet observation, not in the decades that followed. Scientists returned again and again to Voyager's archive, reprocessing old images with new techniques. Each revision revealed new details, faint clouds, previously unnoticed moons, subtle patterns in the magnetic field. Even today, nearly 40 years later, Voyager's data continues to produce discoveries. Its endurance, both mechanical and intellectual, mirrors the slow rhythm of the planet it visited. The mission also redefined how we think about distance. When Voyager 2 transmitted its final images of Uranus, the signals traveled for nearly 3 hours before reaching Earth. Each photon of data crossed billions of kilometers of empty space, a faint whisper arriving from the edge of sunlight. That whisper continues still, as Voyager 2, now far beyond Neptune, sends back occasional reports from interstellar space, a reminder that even what departs can remain connected. Uranus may have seemed calm, but Voyager's fleeting glimpse showed that beneath the soft blue lies motion, asymmetry, and quiet power. The calmness was not emptiness, but balance, a different expression of energy. Understanding that hidden equilibrium would soon lead scientists to a deeper question. What keeps Uranus so cold, and why does it radiate almost no heat into space? To explore that mystery, we turn next to the world beneath its gentle light, the coldest planet under the sun. Of all the planets that circle the sun, none is colder than Uranus. Its upper atmosphere reaches temperatures as low as 224 degrees Celsius, the coldest ever measured in the solar system. Even Neptune, farther from the sun, glows faintly with internal heat. Uranus, by contrast, radiates almost nothing. It receives sunlight weaker than a bright moonbeam and emits barely more energy than it takes in. To astronomers, this strange thermal silence has become one of the most enduring mysteries in planetary science. When Voyager 2 flew past Uranus in 1986, scientists expected the planet to emit a gentle warmth, as every other giant planet does. Jupiter, Saturn, and Neptune all radiate 2 or 3 times more heat than they receive from the sun, a sign of the energy stored in their deep interiors. Uranus did not. Voyager's instruments detected no measurable excess heat at all. It was as if the planet's internal furnace had been extinguished. The cause of that stillness remains uncertain. Some scientists propose that a massive collision long ago knocked Uranus onto its side and released much of its primordial heat into space. Others suspect that its layered interior acts as insulation, trapping heat so efficiently that little escapes. Either way, the result is the same: a planet that has cooled almost to the cosmic background around it, turning slow and quiet over billions of years. To understand why, one must look beneath its calm blue surface. Uranus is classified as an ice giant, distinct from the gas giants Jupiter and Saturn. Instead of vast envelopes of hydrogen and helium, Its bulk consists of heavier materials, water, ammonia, and methane, compressed into exotic forms by immense pressure. These are not ices as we know them, but hot, dense fluids, neither solid nor gaseous, forming layers thousands of kilometers thick. Deep inside, temperatures rise above 5,000 degrees Celsius. Yet that heat remains hidden, unable to escape. The key may lie in stratification, the separation of layers by composition and temperature. If heavy materials sink while lighter ones rise, convection can carry heat upward. But if the layers remain stable, heat becomes trapped below, like warmth beneath a heavy blanket. Models suggest that Uranus's internal layers may be arranged in just such a stable configuration. Dense mixtures of water and ammonia locked under lighter hydrogen, forming a barrier that prevents convection. This could explain the planet's faint glow, or rather, its lack of one. Methane, abundant in the upper atmosphere, adds another layer of complexity. It absorbs sunlight strongly in red wavelengths, giving Uranus its soft blue color, but also contributes to cooling by re-radiating heat efficiently in infrared. The result is a world that reflects much of what little sunlight it receives and loses the rest through slow infrared emission. In thermal balance, Uranus becomes almost invisible to heat itself, a mirror of cold light drifting through space. Despite its chill, the atmosphere remains dynamic. Voyager's instruments measured winds exceeding 700 kilometers per hour, racing in narrow bands from east to west. Later observations with the Hubble Space Telescope and Earth-based infrared telescopes revealed faint storms and shifting clouds, their motion slow but steady. These winds, driven not by internal heat, but by solar energy, represent one of the most efficient weather systems ever observed, proof that even minimal sunlight can sustain motion on planetary scales, high in the stratosphere. Ultraviolet light from the sun splits methane molecules, producing a haze of hydrocarbons that drifts downward like smoke. This thin veil gives Uranus its muted, uniform appearance, a pale cyan glow without visible contrast. Deeper down, invisible to ordinary light, layers of methane, ammonia, and water vapor mix and condense into faint cloud decks. Seen through infrared eyes, these layers shimmer with subtle gradients, showing that the planet's calm surface conceals motion, temperature shifts, and evolving patterns. It is a form of activity measured not in hours or days, but in decades. The coldness of Uranus also affects its magnetic field and rings. At such low temperatures, charged particles move sluggishly, shaping a magnetosphere that behaves unlike any other. Radiation belts around the planet are weak, and auroras, though present, are faint and unpredictable. The cold plasma that fills Uranus's magnetosphere responds more to the planet's rotation than to the solar wind, producing a magnetic rhythm, unlike the steady pulses of Jupiter or Saturn. Even the thin rings, made of dark carbon-rich ice, may owe their stability partly to the planet's low thermal energy, which keeps dust and gas from escaping into space. Yet the most puzzling question remains: why is Uranus colder than Neptune? Both planets are similar in size and composition, yet Neptune emits roughly 2.5 times more heat. The best explanation may lie in history. A violent impact early in Uranus's formation could have mixed its materials unevenly, tilting the planet and altering the flow of energy inside. That same event may have created the internal layering that now locks in its heat. What was once an explosion of motion became a structure of stillness. In another sense, Uranus's coldness is not emptiness, but equilibrium, a state of near-perfect balance between sunlight and emission. It has reached thermal peace, releasing energy only as slowly as it receives it. Over billions of years, that balance may have preserved the planet's fragile rings, stabilized its atmosphere, and shaped the slow rhythm of its seasons. It is a reminder that stillness in nature often hides intricate structure. Today, telescopes continue to probe Uranus's chill depths with increasing precision. The James Webb Space Telescope has captured faint infrared emissions that trace the distribution of methane and water across its hemispheres, helping scientists model how temperature and chemistry vary with altitude. Each new observation refines the picture, not a dead planet, but a delicately balanced one, a world of motion sustained at the threshold of energy. The story of Uranus's coldness is ultimately a story about contrast. It teaches that silence can hold complexity, and that equilibrium can be as revealing as turbulence. Where Jupiter shouts and Neptune stirs, Uranus whispers. Its calm is not absence, but endurance, a quiet persistence shaped by time and physics alike. Not yet the planet's tilt, more extreme than any other, adds another layer of mystery. Because Uranus spins on its side, the rhythm of its seasons unfolds in ways unlike anywhere else. Sunlight and darkness trading places over decades, poles becoming equators, warmth shifting with celestial geometry. To understand how this sideways rotation shapes everything from its atmosphere to its magnetism, we turn next to a planet that rolls through space. Among all the planets orbiting our sun, Uranus moves in a way that defies expectation. Its rotation axis lies almost in the plane of its orbit, tilted by about 98 degrees. In practical terms, this means the planet doesn't spin upright like Earth or Mars. It rolls around the sun on its side, as if it had been gently knocked over and never stood up again. Each pole spends decades pointed directly toward the sun, while the equator lies in shadow. The result is a world with seasons unlike any other known in the solar system. To picture this geometry, imagine a globe spinning while nearly resting on its side. During one half of its orbit, the South Pole faces the sun and basks in continuous light for more than 40 Earth years. During the next half, the North Pole takes its turn, while the opposite side remains in unbroken night. At the equinoxes, when the sun crosses the planet's equator, Uranus briefly experiences something resembling a normal day and night cycle, but it lasts only a few years before the slow lean of its orbit tilts it back again. Each full orbit around the sun takes 84 Earth years, so a single Uranian season spans more than 2 decades. Cause of this extreme tilt has been debated since Voyager 2 revealed it clearly in 1986. The leading explanation points to a giant collision early in Uranus's formation. Billions of years ago, when the solar system was still filled with protoplanets and debris, an object perhaps the size of Earth may have struck Uranus obliquely. The impact could have tipped the young planet sideways, rearranging its internal layers and possibly altering the distribution of its moons and rings. Computer simulations show that such a collision could also explain the strange magnetic field, tilted, off-center, and irregular. In planetary science, the tilt is not merely a curiosity. It is evidence of a violent past, frozen into geometry. Yet the tilt does more than shape history. It dictates the behavior of sunlight and atmosphere. Because the poles alternately face decades of day and decades of night, solar energy is distributed unevenly across the surface. During polar summer, one hemisphere receives constant sunlight, while the other cools in prolonged darkness. However, observations show that the planet's temperature differences are surprisingly small. Even the winter pole remains nearly as warm as the sunlit one. This suggests that Uranus's upper atmosphere efficiently redistributes heat through massive global winds and slow-moving circulation cells. The entire atmosphere functions as a balancing mechanism, smoothing out extremes created by the tilt. Astronomers have measured these winds using Doppler shifts, slight changes in the frequency of light caused by motion. At certain latitudes, air currents flow eastward at speeds exceeding 800 kilometers per hour. Closer to the poles, the motion reverses, creating a complex pattern of alternating jets. Because of the planet's orientation, these winds sweep almost vertically relative to the sun's rays. Seen from space, Uranus appears calm, but beneath that appearance lies a dynamic network of movements shaped by its sideways spin. In the long polar twilight, storms and hazes drift slowly around the planet, responding to a rhythm stretched over decades rather than days. The tilted axis also affects the planet's magnetic field. Most planetary magnetic fields roughly align with the rotation axis, but Uranus's field is offset by thousands of kilometers from the center and inclined by about 60 degrees. As the planet rotates, the magnetosphere, the bubble of magnetic influence, doesn't rotate smoothly. It wobbles, flips, and twists like a lantern swinging in the dark. This constant motion produces unusual auroras near the poles, though they appear in unexpected locations, often far from where magnetic activity occurs on Earth or Jupiter. These auroras were first detected by Voyager 2 and later confirmed by the Hubble Space Telescope. They are faint, ephemeral arcs of ultraviolet light, shimmering for hours before fading again. One of the few visible traces of Uranus's hidden dynamics. For the moons orbiting Uranus, the tilt has profound consequences. They circle around the planet's equatorial plane, which means they too are tilted relative to the solar system's plane. From the sun's perspective, their orbits are almost perpendicular to everything else. When the planet's poles point toward the sun, half the moons move through extended daylight, while the others travel in shadow. At the equinox, sunlight strikes the rings and moons edge on, casting long, thin shadows that sweep across their surfaces. During these rare alignments, astronomers can observe mutual eclipses and occultations, moments when the moons pass in front of or behind one another, briefly dimming or brightening as seen from Earth. These events provide precise data about their orbits and masses, helping scientists refine models of the Uranian system. The rings themselves share this tilted geometry. Composed of dark, radiation-processed material, they are thin and sharp, circling the planet like narrow bands of ink. When viewed from Earth, their brightness changes dramatically depending on orientation. At certain points in the orbit, they nearly vanish, reflecting so little light that the planet seems ringless. Years later, as the tilt brings them back into view, they reappear as delicate arcs. This slow oscillation of perspective gives Uranus a visual rhythm, almost like breathing, widening, narrowing, disappearing, and returning again. It is one of the quiet patterns that define the planet's long dance through space. The tilt also affects how scientists interpret the planet's internal structure. If the axis was indeed the result of a colossal impact, that event might have displaced part of the planet's core and created regions of different density. These irregularities could influence the magnetic field and the way heat moves outward. Some researchers suggest that the same event responsible for the tilt might have sealed the deep interior, preventing heat from escaping, a connection between orientation and temperature that ties directly back to Uranus's extreme cold. In this sense, the sideways spin is not just a visible oddity, but a physical record of internal change. Despite its unusual rotation, Uranus remains gravitationally stable. Simulations show that its current orientation could persist for billions of years. The tilt does not cause wobbling that would threaten its orbit, nor does it lead to chaotic motion of its moons. Instead, the entire system, planet, rings, and satellites, moves together as a single inclined family, maintaining balance in its own tilted frame. This stability in such a strange orientation illustrates how many different forms order can take in nature. Even a planet lying on its side finds equilibrium, because Uranus's rotation period is about 17 hours and 14 minutes. Its day is not much longer than Earth's, but the direction of sunlight across its surface is entirely different. During summer at one pole, the sun appears fixed in the sky, tracing a small circle for 21 years. At the opposite pole, darkness reigns for the same duration. Near the equator, dawn and dusk blend into one another, as the sun glides low along the horizon before vanishing again. These slow changes create an environment where time, light, and shadow lose familiar meaning. For future explorers, a day on Uranus would feel less like a cycle and more like a slow, endless transition between phases of illumination. Understanding this geometry helps scientists interpret long-term climate changes. Because the poles receive direct sunlight for decades, they gradually warm, building up layers of haze and cloud particles. When seasons shift, those layers cool and descend, altering the reflectivity of the planet. This may explain why telescopes have observed Uranus gradually brightening in certain regions over the past 30 years. We are witnessing the slow turning of its tilted seasons. The process is so gradual that a single human lifetime can barely capture half of it. Astronomers are now planning to observe Uranus continuously through the coming equinoxes, hoping to see how the atmosphere responds as the sun moves from pole to pole. They expect to witness new cloud patterns emerging at mid-latitudes, subtle changes in wind direction, and variations in methane abundance. Each of these measurements contributes to understanding how the planet maintains stability despite such uneven solar input. If a future orbiter arrives in the 2040s, it may be able to watch the full transition unfold. From one hemisphere's night into another's dawn, there is a quiet fascination in watching a world that moves so differently. Uranus reminds us that equilibrium does not always mean symmetry. It has found a way to turn sideways through space while remaining serene, following a rhythm written billions of years ago. Its tilt, once a violent scar, has become its defining grace, a slow rotation that shapes light, wind, and magnetism into a single coherent motion. The next step in this calm exploration leads naturally from geometry to rhythm. If Uranus rolls through space like a tilted gyroscope, then its seasons unfold like a slow pulse, stretching across generations. In the following chapter, we will look more closely at this long cycle of light and darkness, the rhythm of Uranian seasons. Seasons on Uranus do not follow the familiar rhythm of Earth. They unfold on a scale so long and gradual that even a lifetime barely spans a single cycle. A full Uranian year lasts 84 Earth years, meaning that each of its 4 seasons endures for about 21 years. Spring, summer, autumn, and winter are not moments of quick transition, but eras of light and shadow, shaped by the planet's unique tilt and slow orbit. Because Uranus spins on its side, each pole faces the sun directly for decades, while the other remains in continuous darkness. When the southern hemisphere is in summer, sunlight falls almost vertically onto the South Pole, creating a long, unwavering day that never sets. At the same time, the northern hemisphere lies in night so deep that even the faint scattering of sunlight by the rings cannot brighten it. When the planet reaches the opposite side of its orbit, the situation reverses. The North Pole begins its decades of daylight, and the south sinks into the cold of night. Only around the equinoxes, occurring once every 42 years, does Uranus experience something similar to our familiar alternation of day and night. From an earthly perspective, this is difficult to imagine. 21 years of sunrise without sunset, followed by 21 years of darkness without dawn. For the atmosphere, however, this slow rhythm is not peaceful. It drives deep, planet-wide changes in temperature, cloud structure, and circulation. Because the poles are exposed to constant sunlight for such long periods, they slowly absorb energy, forming layers of haze and high-altitude clouds. When the season changes, those hazes cool, sink, and dissolve, while new ones appear in the hemisphere emerging from night. Seen from afar, Uranus gradually changes brightness and hue over the decades, reflecting the slow dance of illumination across its surface. Modern observations have allowed scientists to watch parts of this cycle unfold in real time. When Voyager 2 visited in 1986, the planet's southern hemisphere was in full summer, its pole brightly lit. The northern hemisphere was completely hidden in darkness. As years passed and Uranus moved toward its equinox in 2007, telescopes on Earth and in orbit, including Hubble and Keck, recorded a steady increase in cloud activity in the northern hemisphere. Bright storms and subtle bands began to appear where none had been seen before, while the southern regions dimmed. This gradual shift marked the planet's slow turning from one hemisphere's summer to the other's spring. The temperature difference between day and night sides of Uranus remains surprisingly small, rarely more than a few degrees. This indicates that the planet's atmosphere is extraordinarily efficient at redistributing heat. Winds carry energy around the globe, mixing air from sunlit and dark regions. This slow, steady circulation prevents extreme temperature contrasts despite the uneven exposure to sunlight. It is as if the entire atmosphere breathes together, maintaining balance through motion rather than stillness. The behavior of clouds during these long seasons reveals the complexity of Uranus's climate. The upper atmosphere contains layers of methane ice crystals, forming faint, hazy decks. Deeper layers may contain ammonia and hydrogen sulfide, condensed into tiny droplets under immense pressure. As sunlight increases in a given hemisphere, these compounds sublimate and rise, creating new clouds and reflective patches. During the long polar nights, they cool and settle, creating darker regions. Infrared observations show that the energy absorbed during decades of sunlight penetrates slowly downward, influencing weather patterns long after a pole has turned away from the sun. In this way, each season leaves a memory that shapes the next. One of the most remarkable features of this rhythm is its delay. Because Uranus rotates so slowly around the sun, its atmosphere reacts with inertia. Peak temperatures often occur years after the maximum sunlight. This is similar to Earth's oceans, which warm gradually after summer begins and cool long after autumn sets in. But on Uranus, this lag lasts decades. The northern hemisphere, currently moving into full summer, may still be absorbing the residual warmth of the southern one. This overlapping of thermal memory gives Uranus a kind of long planetary heartbeat, pulsing softly every few decades. Astronomers are now mapping these seasonal variations with precision. By observing reflected sunlight in different wavelengths, they can estimate cloud altitudes and the composition of haze layers. During the approach to the 2007 equinox, the Hubble Space Telescope detected bright white storms near the equator, transient systems, possibly fueled by the contrast between hemispheres' switching roles. In subsequent years, the Keck Observatory recorded methane cloud bands forming at mid-latitudes, showing that the atmosphere responds slowly but persistently to changing light conditions. Each observation adds a frame to a planetary time-lapse that will take more than a century to complete. Because the poles spend so much time illuminated, scientists expected them to be much warmer than the equator. Yet measurements show that temperatures are nearly uniform across latitudes. This puzzling stability suggests that winds, which blow predominantly eastward, distribute energy efficiently from pole to pole. The circulation cells stretch deep into the atmosphere, forming layers where gases rise in one region and sink in another, maintaining global balance. This mechanism likely explains why Uranus's weather, though slow, can still produce sudden storms. The long accumulation of energy eventually breaks into motion. The gradual rhythm of the seasons also affects the planet's magnetic field and radiation environment. When the poles face the sun, the orientation of the magnetic field relative to the solar wind changes dramatically. At certain points in the orbit, the magnetosphere opens like a door, allowing charged particles from the sun to enter and create auroras near the poles. At other times, the field is closed and stable, shielding the planet completely. These cyclic changes occur on a timescale measured not in hours, as on Earth, but in decades. They contribute to a subtle pattern of radiation around Uranus that evolves as slowly as its seasons. The planet's moons and rings experience their own versions of these long cycles. During the solstices, one side of each moon receives sunlight for years, while the other lies in darkness. This produces temperature differences that may affect surface ice and possibly influence internal activity. When the equinox arrives, sunlight strikes the equatorial plane directly, illuminating the ring's edge-on and casting narrow shadows across the planet's atmosphere. For astronomers, these moments are invaluable. They allow precise measurements of ring thickness and composition. Such observations can happen only twice per Uranian year, roughly once every 4 decades, making each one a rare scientific opportunity as of the early 2020s. Uranus is moving deeper into its northern summer. The North Pole now faces the sun, and for the next 20 years, it will remain bathed in continuous light. Scientists expect that new cloud systems will emerge, brightening the hemisphere and altering the planet's albedo. When a future mission, perhaps the planned Uranus orbiter and probe, arrives in the 2040s, it will observe the planet near the height of this summer. By then, the southern hemisphere will have spent decades in darkness, waiting for the slow return of dawn. This alternating pattern defines the rhythm of Uranus's life, a celestial pendulum swinging so slowly that each motion echoes across generations. Studying these immense seasonal changes teaches scientists about energy balance, how planets absorb, store, and release heat over time. The lessons extend beyond Uranus. Many of the exoplanets discovered around distant stars are similar in size and composition, and understanding Uranus's slow climatic rhythm helps interpret their observed temperatures and brightness variations. In this way, the far-off blue world continues to inform our understanding of planetary atmospheres. Across the galaxy, there is something quietly humbling in these timescales. Where Earth's weather changes daily and seasons shift in months, Uranus moves in decades. Its atmosphere carries the memory of light from generations past, turning slowly toward new illumination. In that rhythm, one can sense how patience becomes a scientific necessity, how observation over lifetimes is required to understand a world that measures time in centuries rather than years. And yet, even within this slow rhythm, motion never ceases. Winds still flow, storms still form, and clouds drift endlessly around the tilted sphere. They respond to sunlight faint but persistent, maintaining the fragile balance that keeps the planet alive in its distant orbit. These winds, invisible from afar but vital to the planet's equilibrium, form the next part of Uranus's quiet story. To understand how this cold, distant world breathes and circulates, we turn next to winds in the shadow of the sun. From a distance, Uranus appears perfectly calm, a soft blue sphere with almost no visible features. But beneath this quiet appearance, its atmosphere is alive with motion. Powerful winds circle the planet, shaping faint bands and clouds that drift slowly around the globe. In the cold, thin sunlight that reaches it, Uranus maintains one of the most complex atmospheric systems in the solar system, one that moves with strength, yet reveals itself only through patience and careful observation. The discovery of these winds began long after Voyager 2's brief visit. During the 1986 flyby, the spacecraft's cameras saw almost no structure. At that time, the southern hemisphere was fully illuminated, and sunlight fell directly on the pole. The lighting flattened contrasts, hiding most features from view. Voyager's team assumed the atmosphere was largely inert, a still layer of hydrogen, helium, and methane, too cold to produce much motion. For more than a decade, that view remained unchallenged. Then, in the early 2000s, as Uranus approached its equinox, new telescopes began to see something different. Infrared imaging revealed bright, high-altitude clouds forming near the equator and drifting across latitudes over months. They were small compared to Jupiter's massive storms, but their persistence was striking. Each bright patch marked a region where methane condensed into ice crystals carried by high-velocity winds. By tracking their movement, astronomers measured the planet's atmospheric rotation, and the results were astonishing. At mid-latitudes, Uranus's winds blow eastward at speeds of 500 to 800 kilometers per hour. Near the equator, they slow and even reverse direction, moving westward instead. This alternating pattern, fast at the poles, slower near the middle, creates complex jet streams that circle the planet in both directions. It is a delicate balance between solar heating, rotation, and internal dynamics. Unlike on Earth, where sunlight drives weather on a daily cycle, Uranus's faint energy input means that each wind pattern persists for years or even decades. Slowly evolving as the planet moves along its orbit, the structure of these winds is shaped by the planet's tilt. Because Uranus rolls on its side, sunlight falls differently across its atmosphere than on any other planet. When one pole faces the sun, the other remains in shadow for decades, creating long gradients of temperature and pressure. These gradients set the air in motion, driving winds that circle the planet vertically relative to the solar plane. The result is a three-dimensional system, layers of gas moving in different directions depending on depth and latitude. Infrared observations suggest that the upper atmosphere, where methane forms hazes, moves fastest, while deeper layers remain slower and more stable. Even at such great distance from the sun, Uranus's winds rival those on much larger planets. The key lies in its rotation speed. Despite its slow orbit, Uranus completes a day in just 17 hours and 14 minutes. This rapid spin generates strong Coriolis forces, curving the paths of moving gases and organizing them into stable bands. It's the same principle that creates jet streams on Earth, but operating on a planetary scale. The combination of fast rotation and long seasonal cycles produces winds that are both powerful and enduring, a quiet engine running steadily in the background of the solar system. The planets' low internal heat adds another layer of intrigue. On Jupiter and Saturn, rising hot gases feed enormous storms. Uranus lacks that source of energy, yet its winds remain strong. How can a world so cold and thermally quiet maintain such motion? One explanation points to solar energy absorbed and stored over decades. During long polar summers, sunlight penetrates deep into the upper atmosphere, warming it slowly. As the planet turns and seasons shift, that stored energy redistributes toward the darker hemisphere, driving broad planet-wide flows. The process is inefficient but steady, maintaining wind speeds that change only slightly over time. Some scientists compare Uranus's atmosphere to a vast, slow-moving ocean, stratified, layered, and flowing in multiple directions at once. Clouds form at boundaries between these layers, tracing the invisible paths of convection. Most of these clouds are made of methane ice, shining faintly in near-infrared wavelengths, but nearly invisible to the human eye. Underneath, there may be deeper levels composed of ammonia or hydrogen sulfide, forming liquid or slushy droplets under pressure. These layers likely slide past each other, producing the smooth banding that telescopes have only recently begun to resolve. In 2014, the Keck Observatory captured one of the most remarkable events ever seen on Uranus, a bright storm nearly 10,000 kilometers wide, towering through the atmosphere. The storm's brightness suggested that it extended high into the methane layer, reflecting sunlight with unusual intensity. Scientists were surprised. Uranus was near equinox, a time when sunlight was evenly distributed between hemispheres, and such storms were not expected. The event hinted that deep processes, not just solar heating, influenced the planet's weather. Even in apparent stillness, Uranus can release sudden bursts of energy. The persistence of winds in such conditions challenges our understanding of atmospheric physics. Without significant internal heat, circulation should weaken over time. Instead, Uranus maintains its momentum, as if conserving energy from a long-forgotten source. Some researchers propose that residual heat remains trapped in mid-layers of the planet, occasionally escaping as convection cells that reach the surface. Others suggest that mechanical mixing, the slow transfer of motion between layers, sustains the winds like a flywheel, long after the original impulse has faded. Both ideas imply that Uranus's interior and atmosphere are tightly coupled, exchanging energy in ways we cannot yet observe directly. To study these dynamics, astronomers rely on subtle techniques. By monitoring tiny shifts in reflected light, they measure how clouds move relative to the planet's rotation. Computer models simulate how methane condenses and sublimates, producing cycles of cloud formation that match observed patterns. Infrared data from the James Webb Space Telescope now reveal temperature variations across latitudes, helping to identify the sources of motion. In these observations, Uranus emerges not as static, but as deeply alive, a world whose motion is too slow for human senses, but continuous on planetary time. The winds also interact with the planet's magnetic field. As charged particles flow through the upper atmosphere, they can influence the distribution of haze and cloud particles. The tilted magnetic field rotates out of alignment with the planet's spin, modulating how the solar wind enters the atmosphere. This interaction may produce periodic surges in auroral activity and subtle heating in localized regions. Such processes could explain why some parts of Uranus's atmosphere appear warmer than models predict. Small bursts of energy generated by electromagnetic friction in the shadow of the sun. What makes Uranus's winds remarkable is not just their strength, but their consistency. Over decades of observation, the same broad bands have remained in nearly the same positions. Storms rise and fade, but the global pattern endures. It is as though the planet has found a state of motion that resists change, a long equilibrium between sunlight, rotation, and chemistry. This steadiness gives Uranus a kind of elegance, a quiet balance between forces that, elsewhere, would produce chaos. Even so, the atmosphere is not entirely predictable. Astronomers expect that as Uranus moves deeper into its northern summer, the distribution of clouds and winds will shift again. New storms may appear in regions now dormant, while older features vanish into darkness. Each decade brings subtle changes that, when viewed together, form the slow choreography of an alien climate. By continuing to watch these changes, scientists hope to link the visible patterns to deeper processes, to find the connection between wind, temperature, and the unseen layers below. In studying Uranus's atmosphere, researchers often describe it as an expression of balance under constraint. With almost no internal heat, minimal sunlight, and extreme tilt, the planet should be quiet. Instead, it sustains constant motion, not loud or violent, but persistent and organized. This quiet motion is a reminder that energy can take many forms, and that even in the outer darkness, equilibrium is never truly still. The winds of Uranus are, in a sense, the planet's slow heartbeat, a steady pulse that continues despite the cold. But the atmosphere tells only half the story. To understand why these winds exist at all, and how they maintain themselves without visible energy sources, we must look inward. Beneath the clouds, deep inside Uranus, lies a world of strange materials: water, ammonia, and methane compressed into exotic states that defy ordinary physics. It is there, perhaps, that the planet's hidden energy still lingers, shaping everything above it. In the next chapter, we descend into that unseen world to explore hidden heat, the mystery of Uranus's interior. When Voyager 2 measured the temperature of Uranus in 1986, one fact stood out more than any other. The planet was almost completely dark to infrared instruments. Unlike Jupiter, Saturn, or even Neptune, Uranus emitted no measurable excess heat. The energy it radiated matched almost exactly the sunlight it absorbed. For planetary scientists, this was a puzzle. Every other giant planet glows faintly in infrared, releasing the leftover warmth of its birth, the slow cooling of primordial heat trapped since the solar system's formation. Uranus, by contrast, seemed to have gone quiet inside, as if its inner furnace had been extinguished billions of years ago. That mystery still endures. To this day, Uranus remains the only major planet without detectable internal heat flow. It is colder than expected for its distance from the Sun, colder even than Neptune, which lies farther out. Understanding why requires descending, conceptually, into the planet's hidden interior, a region that no spacecraft has ever seen and that resists easy modeling. The structure of Uranus is inferred from gravity, magnetism, and theoretical calculations. At the top lies the visible atmosphere, composed mostly of hydrogen, helium, and a small fraction of methane. Below that begins what scientists call the mantle, not a solid layer, but a vast region of water, ammonia, and methane under extreme pressure. These substances exist not as ordinary liquids or gases, but in exotic intermediate states. Under millions of atmospheres of pressure and temperatures reaching thousands of degrees, they form dense ionic fluids that conduct electricity. Deeper still, toward the center, lies a rocky core made of silicates and metals, perhaps similar in size to Earth, but compressed beyond recognition. In Jupiter and Saturn, heat from the deep interior rises outward through convection, hot material moving upward, cool material sinking down. This churning carries energy efficiently, feeding strong weather systems and magnetic fields. Uranus seems to lack such motion. Its interior is believed to be stratified, divided into layers of slightly different composition and density. Each layer acts as a barrier, preventing the flow of heat between regions. Warmth from the core remains trapped below, unable to reach the atmosphere. Over billions of years, the outer layers radiated away their energy, leaving the planet's surface frigid, while the deep interior stayed insulated and quiet. This layered structure may have been created by a massive collision early in Uranus's history, the same event that tipped the planet onto its side. A glancing blow from a large protoplanet could have mixed and redistributed materials unevenly, forming complex gradients of composition. The denser layers sank, while lighter compounds rose, but they never fully blended. Such an impact might also have disrupted convection, locking heat deep within. If this is true, Uranus is not cold because it never had energy, but because it cannot release it anymore. Its silence is a kind of geological memory, a trace of violence preserved as stillness. Another hypothesis focuses on the thermal conductivity of the mantle materials. Under extreme pressure, mixtures of water, methane, and ammonia may become superionic. In this state, oxygen atoms remain in a fixed lattice, while hydrogen ions flow through them freely, like an electrical fluid. Superionic ices are thought to be viscous and sluggish, transferring heat very slowly. If large portions of Uranus's interior exist in this phase, they could effectively block convection. The heat would be trapped not because of layering, but because the material itself conducts energy inefficiently. Recent high-pressure experiments on Earth support this idea, producing superionic water at pressures similar to those inside Uranus. The discovery of such states of matter has changed how scientists imagine the interiors of ice. Giant worlds where ice behaves more like metal than solid crystal. Despite the name, the interior of Uranus is not uniformly cold. Models suggest that deep inside, temperatures may exceed 5,000 degrees Celsius, hotter than the surface of the sun's photosphere. But that heat remains hidden, sealed beneath kilometers of dense, conductive layers. Only the faintest fraction escapes to the atmosphere, leaving the outer world frozen. It's a paradox, a planet with a hot heart and an icy skin. This separation between interior and exterior defines Uranus more than any single feature. If we could descend through its atmosphere, the environment would change gradually but relentlessly. At first, light blue clouds of methane would fade into darkness. Pressure would increase, compressing gas into liquid-like densities. Hydrogen and helium would mix with heavier molecules, forming an opaque fluid with no clear boundary between air and sea. At a depth of several thousand kilometers, the pressure would reach millions of atmospheres, and the temperature would rise to thousands of degrees. In that zone, the mixture of water and ammonia likely becomes electrically conductive, the region believed to generate the planet's magnetic field. Unlike Earth, where magnetism arises from a molten iron core, Uranus's field probably comes from this vast, slushy ocean of ions. That difference explains much of Uranus's magnetic irregularity. Because the conducting layer is shallow and asymmetric, the resulting magnetic field is tilted, offset, and uneven. It doesn't align with the planet's center or spin axis, producing a magnetosphere that wobbles chaotically as Uranus rotates. In this way, the hidden interior, silent in heat, still expresses itself through magnetism, shaping the surrounding space environment. The invisible currents within create a field so misaligned that, to an outside observer, it seems to pulse as the planet turns. This phenomenon connects the deep interior directly to the upper atmosphere and rings, linking the unseen to the visible. Understanding Uranus's interior is crucial not only for its own sake, but also for what it reveals about planetary formation. Ice giants like Uranus and Neptune represent a distinct category of planets, neither rocky like Earth nor gaseous like Jupiter. They are rich in volatile compounds, formed in regions of the solar system where temperatures were low enough for water, methane, and ammonia to freeze. Studying their internal structure helps explain how common such worlds might be elsewhere. Exoplanet surveys have found hundreds of planets similar in size to Uranus, suggesting that ice giants are one of the most frequent planetary types in the galaxy. By deciphering Uranus's hidden heat, scientists are learning how energy flows and freezes across the universe. The challenge lies in testing these models. Remote observations can only probe the outermost layers. To understand what lies deeper, scientists rely on indirect clues, gravity fields, magnetic measurements, and small variations in atmospheric motion. Each new dataset refines the models, narrowing the possibilities for what materials exist and how they behave. Future missions, particularly the planned Uranus orbiter and probe, could transform this understanding. An atmospheric probe descending into Uranus could measure temperature and composition directly, while an orbiter could map the gravity field with precision, revealing how mass is distributed inside. Such a mission would finally allow us to compare models with reality, turning decades of inference into evidence. There is a subtle beauty in this mystery. Uranus, from the outside, seems serene and inert, yet inside it holds immense energy, motionless not because it lacks power, but because that power is locked away. The planet teaches a quiet lesson about the nature of systems in equilibrium. Even when heat cannot escape, structure and balance persist. The stillness of Uranus is not emptiness. It is containment. Like a slow ember beneath layers of ash, its interior still glows, unseen but enduring. Scientists often describe the study of Uranus as a reminder of humility. We know the shape of its orbit, the color of its clouds, even the direction of its winds, but we do not yet know what truly lies beneath. To understand it fully, we must look beyond what is visible and imagine the physics of materials that barely exist on Earth. Every experiment in high-pressure chemistry, every new telescope observation brings us closer to unveiling this hidden world dot. The next great questions flow naturally from here. If the planet's magnetic field arises from this shallow, asymmetric ocean of conducting fluids, how exactly does it behave? Why does it tilt so dramatically? And how does it evolve over time? These questions lead from the heat trapped within to the magnetic forces that extend far beyond, an invisible architecture connecting Uranus's deep interior to space itself. In the following chapter, we turn to that field of shifting lines and wandering poles to explore magnetic fields at odd angles. Every planet in the solar system possesses its own invisible structure, a magnetic field that surrounds and protects it. These fields are born deep within planetary interiors, generated by the motion of electrically conductive materials. On Earth, the churning of molten iron in the outer core produces a magnetic field aligned roughly with the planet's rotation axis. The same principle applies to Jupiter and Saturn, where metallic hydrogen moves in vast currents, creating powerful magnetic bubbles that extend millions of kilometers into space. But Uranus, once again, breaks the pattern. Its field does not follow symmetry, logic, or even common sense. It is a magnetic system so misaligned offset and unstable that it behaves almost like two separate fields competing for control. When Voyager 2 passed Uranus in 1986, one of its tasks was to measure magnetic and charged particle data during the flyby. The results astonished the mission team. Instead of a field centered within the planet, and tilted slightly from the axis of rotation, as expected. The magnetic field of Uranus was shifted by nearly 8,000 kilometers from the planet's center and tilted by 59 degrees relative to the rotation axis. This meant that the magnetic north and south poles were nowhere near the geographic poles. As the planet rotated, the field lines did not move smoothly but twisted, swung, and wobbled dramatically, creating a magnetosphere that changed shape every few hours. It was as though Uranus carried a magnetic field built on a lopsided foundation. The discovery puzzled scientists for decades. How could such a geometry exist, and how could it remain stable over time? The key lies in where the field is generated. On Earth, the magnetic field originates near the planet's core, deep, dense, and nearly spherical. But in Uranus, the conducting layer is believed to be much shallower. It likely forms in the mantle region, composed of water, ammonia, and methane under immense pressure. These materials become electrically conductive when compressed into an ionic or superionic state, allowing currents to flow. However, because the layer is not uniform, thicker in some regions, thinner in others, the resulting magnetic field emerges from off-center zones rather than from the core. It is as if the dynamo that drives magnetism is floating inside the planet, tilted and displaced. This model helps explain the irregularities measured by Voyager 2. The spacecraft's magnetometer detected rapid changes in field strength as it passed over the poles, suggesting that the magnetic region is patchy and uneven. Instead of neat, symmetric lines looping from pole to pole, Uranus's field resembles a distorted spiral. In some areas, field lines converge tightly. In others, they spread apart. The field strength near one pole can be up to 10 times greater than near the opposite one. The result is a magnetosphere that defies the usual planetary blueprint, asymmetric, unpredictable, and constantly shifting dot as Uranus rotates on its side. This tilted field performs a kind of cosmic dance. Every 17 hours, the magnetosphere sweeps through space like a turning wheel, alternately exposing its poles and equator to the solar wind. This motion causes the field to open and close repeatedly, allowing streams of charged particles from the sun to enter and escape. During one part of the rotation, the magnetosphere compresses, focusing energy near the poles. During another, it stretches out behind the planet, forming a long tail that twists like a corkscrew. Scientists call this the magnetic tumble, and it gives Uranus one of the most variable space environments in the solar system. Despite this complexity, the field still provides protection. It shields the atmosphere and rings from the harshest solar radiation, although the coverage is uneven. Because of the tilt, some regions remain exposed longer than others. This irregular shielding may influence how particles interact with the rings and moons, subtly changing their chemistry over time. In places where magnetic reconnection occurs, where field lines break and reconnect, energetic bursts of radiation may periodically strike the atmosphere, creating auroras. The auroras of Uranus are unlike those of Earth or Jupiter. They are faint, brief, and unpredictable, often appearing far from the magnetic poles. Voyager 2 detected ultraviolet flashes near mid-latitudes, and later observations by the Hubble Space Telescope confirm similar emissions. These glows are thought to occur when solar wind particles spiral along the tilted magnetic field lines and collide with hydrogen atoms high in the atmosphere. But because the field changes orientation so rapidly, the auroras move too, appearing in new locations from one rotation to the next. To observers, they would seem to flicker across the planet, never anchored, always shifting, a subtle reminder of the unstable geometry that governs. Uranus's space weather. The magnetic field also interacts with the planet's rings and moons in unusual ways. Charged particles trapped in the magnetosphere circulate along field lines, striking the surfaces of nearby moons and altering their chemistry. This process may explain why the inner moons and rings appear unusually dark. Energetic electrons and ions bombard their icy surfaces, turning simple molecules like water and methane into darker, carbon-rich compounds through radiation damage. Over time, these reactions create a thin, sooty coating that absorbs light, giving Uranus's rings their deep charcoal hue. This connection between magnetism and appearance ties the invisible to the visible, linking the planet's hidden interior to its outermost features. One of the most striking consequences of Uranus's tilted magnetosphere is how it interacts with the solar wind throughout its long orbit. For most planets, a magnetosphere faces roughly toward the Sun, forming a predictable bow shock where solar particles are deflected. On Uranus, however, the rotation axis lies almost perpendicular to the orbital plane, meaning the magnetosphere points upward or downward relative to the Sun. As the planet moves along its 84-year path, the direction of the magnetic field relative to the solar wind changes completely. During one part of the orbit, the magnetic north faces the Sun. Decades later, the south does. This alternating orientation produces long-term cycles in how the planet's magnetic environment behaves, perhaps influencing atmospheric chemistry and auroral activity over decades long. Intervals. For planetary scientists, Uranus's magnetic field offers a natural laboratory for understanding the diversity of dynamos across the universe. Until the Voyager era, magnetic fields were assumed to follow a general pattern, roughly aligned with rotation, roughly centered, generated by deep metallic cores. Uranus and Neptune shattered that assumption. Both exhibit tilted, offset, and irregular fields, suggesting that ice giants represent a distinct class of magnetic behavior. Their dynamos are likely shallow and fragmented, driven by partially conductive layers rather than molten cores. Such a mechanism could be common among exoplanets of similar size, meaning that many worlds beyond our solar system might carry fields as chaotic as Uranus's. Studying this tilted magnetism, therefore, is not only about one planet, but about an entire category of worlds. Researchers are now using data from the Hubble Space Telescope and the James Webb Space Telescope to track how Uranus's magnetic field interacts with the solar wind in real time. By observing variations in ultraviolet and infrared emissions, they can infer changes in magnetic geometry. These long-term studies may reveal how the field evolves through the planet's seasons, how it weakens, strengthens, or reorients over decades. Such work requires extraordinary patience, as a single year of Uranus lasts longer than a human lifetime. But each new measurement helps complete a picture of a magnetic system that challenges everything we know about planetary physics. Future missions, like the proposed Uranus orbiter and probe, are designed to solve this mystery. Equipped with advanced magnetometers, plasma instruments, and charged particle detectors, such a spacecraft could map the magnetic field in 3 dimensions over time, tracing how it connects to the interior and to the moons. It could observe auroras directly, measure particle flows, and reveal how the magnetosphere responds to solar storms. In doing so, it would transform our understanding of not just Uranus, but of all planets that live under weak sunlight and complex magnetic geometries. The magnetism of Uranus, though strange and irregular, forms a quiet bridge between the deep interior and the space beyond. It is the unseen extension of the planet's hidden energy, a reflection of its asymmetry, its cold, and its internal history. Through this invisible field, Uranus reveals that even the most tranquil-looking worlds can harbor powerful and unpredictable forces beneath the surface. And orbiting within that magnetosphere, shaped by it and sometimes scarred by its energy, are the moons of Uranus, small, icy worlds that tell their own stories of motion, shadow, and time. To understand the planet fully, we must look next to these companions, each one a silent witness to Uranus's long and tilted journey. In the next chapter, we explore them together. The moons, small worlds of ice and shadow. Uranus is not alone in its quiet orbit. Circling the planet are 27 known moons, each following the tilted plane of the planet's equator. Together, they form a miniature system, an arrangement of icy worlds, suspended within the planet's peculiar magnetic field and faint rings. From the smallest irregular fragments to the large spherical satellites, they create a family that mirrors Uranus itself, calm on the surface, yet full of hidden complexity. The moons of Uranus range widely in size. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were all discovered long before Voyager's visit. Through patient observation from Earth, each of them is between 470 and 1,580 kilometers in diameter, smaller than our moon, but large enough to have their own gravity and geological features. The remaining 22 are smaller, irregularly shaped bodies, likely captured or formed from debris around the planet. They orbit in a thin, flat plane that matches Uranus's rotation, a reminder that the planet's entire system shares its sideways orientation. Unlike Jupiter's volcanic Io or Saturn's active Enceladus, the moons of Uranus appear quiet. Their surfaces are frozen, ancient, and scarred by impacts accumulated over billions of years. Yet beneath this apparent stillness lies subtle variation. Each moon has its own color, brightness, and density, revealing differences in composition. Some contain a mixture of ice and dark carbon compounds. Others are coated with brighter water ice. Infrared observations show traces of ammonia and methane ices, suggesting that chemical interactions with the planet's magnetosphere continue to alter their surfaces today. Voyager 2 provided the first close look at these worlds in 1986. During its brief flyby, the spacecraft photographed the 5 largest moons, revealing landscapes unlike any seen before. Titania and Oberon, the 2 outermost, appeared heavily cratered, ancient terrains frozen in time. Ariel and Umbriel, orbiting closer to the planet, showed smoother plains and deep canyons, hinting at past internal activity. And Miranda, the innermost and smallest of the 5, defied expectations entirely, with cliffs and ridges that looked almost stitched together from separate worlds. Each moon told a slightly different story of formation, heating, and change. Scientists classify the Uranian moons into 3 general groups. The inner moons, numbering 13, are small and irregular, many less than 100 kilometers across. They orbit close to the planet, within or near the ring system, and may act as shepherds that help maintain the narrow rings. These tiny bodies experience constant bombardment by charged particles trapped in Uranus's magnetic field. Over time, this radiation darkens their surfaces, creating a consistent charcoal gray tone. The inner moons likely formed from debris after collisions or from material left over when the planet's original disk condensed. They represent the most fragile remnants of Uranus's history. Beyond them orbit the 5 classical moons, the large, roughly spherical bodies that dominate the system. Each has its own distinctive surface and internal structure, Titania, the largest, shows networks of long faults and troughs that stretch for hundreds of kilometers, evidence of crustal expansion as the moon's interior cooled and contracted. Oberon, the outermost, bears a mix of bright and dark patches, possibly created when impacts exposed cleaner ice beneath a darker crust. Ariel appears younger, with fewer craters and extensive valleys carved by ancient tectonic forces. Umbriel, by contrast, is darker and older, its surface covered in a layer of radiation-altered ice. These contrasts suggest that internal heating and resurfacing processes once varied strongly among the moons, perhaps influenced by their distance from Uranus or by gravitational interactions between them. Some of the largest moons may have once harbored subsurface oceans. Models show that if they contained even small amounts of ammonia or salts mixed with water, those liquids could remain unfrozen beneath thick ice shells for billions of years. Tidal forces, the constant flexing caused by Uranus's gravity, might have generated enough heat to keep these oceans stable. If true, it means that the Uranian system could include hidden reservoirs of liquid water far from the sun, much like Europa or Enceladus. Such environments are of great interest to scientists studying where chemistry, and perhaps life, could exist beyond Earth. Outside the main group lies the outer family of moons, 9 small, irregular satellites orbiting far beyond the planet's rings. These bodies likely did not form with Uranus, but were captured later from the surrounding region of the solar system. Their eccentric, inclined orbits and retrograde motion, some move opposite to Uranus's rotation, support this idea. They are dark, distant, and difficult to study, visible only as faint points even in modern telescopes. Still, their presence helps scientists reconstruct the history of Uranus's gravitational reach, showing how it gathered and shaped material over time. The interactions between Uranus's moons and its magnetosphere create an ongoing exchange of energy and particles. Charged ions spiral along magnetic field lines and strike the moon's surfaces, breaking apart molecules and forming new ones. These processes, known as radiolysis, gradually darken the moons and modify their chemistry. Some regions may even develop thin layers of complex organic compounds created from methane and water ice under radiation. This slow transformation happens over millions of years, a geological evolution driven not by tectonics or volcanism, but by invisible magnetic rain. The dynamics of the Uranian system are intricate. Because the planet's axis is tilted almost completely sideways, the moons orbit in a plane that swings around relative to the sun. During one half of the planet's long year, the northern hemispheres of the moons are in continuous daylight. During the other, continuous darkness. These extreme lighting conditions lead to temperature contrasts on the surface, possibly driving slow cycles of sublimation and frost migration. As sunlight moves from one pole to another, frozen methane and water may vaporize and recondense elsewhere, slowly reshaping surface patterns. This rhythm, though imperceptible in human time, defines the moon's long seasons. The naming of Uranus's moons carries its own quiet poetry. Unlike the mythological names used for most planetary satellites, the moons of Uranus are drawn from the works of William, Shakespeare, and Alexander Pope. Titania and Oberon come from A Midsummer Night's Dream. Ariel and Umbriel from The Rape of the Lock. Miranda from The Tempest. This literary tradition gives the system a distinctive character, connecting the icy silence of space with the language of imagination. It also reflects a long-standing curiosity that these worlds, though distant, carry names that evoke motion, spirit, and likeness. Despite decades of study, Many details about the Uranian moons remain uncertain. We do not yet know their exact compositions, their internal structures, or whether they contain liquid layers. No spacecraft has ever orbited Uranus long enough to watch them over time. Most of what we know comes from the brief glance of Voyager 2 and from telescope images taken decades later. Future missions could reveal how these moons interact, how their orbits evolve, and whether any still retain traces of internal heat. The upcoming Uranus Orbiter and Probe mission, if approved and launched in the 2030s, may finally answer these questions. Equipped with imaging systems, spectrometers, and radar, it could map the surfaces of the major moons in unprecedented detail and search for signs of internal activity. Even a single orbit around Uranus could rewrite what we know about these worlds of ice and shadow. For scientists, this system represents an opportunity to study processes that connect geology, magnetism, and chemistry under conditions unlike any other in the solar system. Among all of Uranus's moons, one stands apart, a world so fractured and unusual that it seems almost assembled from fragments of others. Its cliffs rise higher than any known in the solar system, and its surface looks torn and reassembled, as if shaped by cataclysm. This moon, Miranda, holds clues to the forces that once sculpted the entire Uranian system. To understand the extremes of ice, gravity, and history gathered around Uranus, we turn next to its most enigmatic companion, Miranda, the broken moon. When Voyager 2 approached Uranus in 1986, scientists expected its moons to be quiet, featureless worlds, frozen relics of the early solar system. But as the spacecraft drew near to Miranda, the innermost of Uranus's 5 large moons, what it revealed defied imagination. On the screen appeared a surface torn apart and reassembled, covered with cliffs, ridges, valleys, and vast blocks of terrain that seemed to belong to different worlds. It looked less like a single moon and more like a collage of planetary fragments fused together by chance. The name The Broken Moon would soon follow, a title earned not through poetry, but through geology. Miranda is small, only about 470 kilometers in diameter, roughly 1/7 the size of Earth's moon. Yet within that modest sphere lies some of the most dramatic topography known anywhere in the solar system. The most striking feature is Verona Rupes, a cliff more than 20 kilometers high, twice the depth of the Grand Canyon, and likely the tallest known cliff face in the entire solar system. If someone could stand at its edge and drop a rock, it would fall for 10 minutes before reaching the ground. Such extremes invite the question, how could a moon so small generate landscapes so vast and violent? The surface of Miranda is divided into large, irregular regions known as coronae, enormous oval structures bordered by ridges and troughs. Voyager 2 identified at least 3 major coronae, Arden, Elsinore, and Inverness, each tens to hundreds of kilometers across. Between them lie older, heavily cratered plains. These coronae are unique. No other moon shows terrain quite like them. They appear to be areas where the crust of Miranda has been pulled, stretched, and reshaped, possibly by internal forces or by catastrophic events long ago. The patterns are so intricate that they resemble frozen waves of motion, geological scars locked in ice. Two main theories compete to explain Miranda's fractured surface. The first suggests that tidal heating played a crucial role. In the distant past, Miranda may have been caught in orbital resonances with Uranus's other moons, such as Ariel or Umbriel. These gravitational interactions could have forced the small moon's orbit to become slightly elliptical, causing it to flex and heat internally as it moved closer to and farther from Uranus. Over time, that internal heat would have melted parts of the icy mantle, leading to tectonic uplift and partial resurfacing. The coronae might mark areas where warm material from below pushed upward, cracking and rearranging the crust. The second theory is even more dramatic. Miranda may have shattered and reassembled. According to this model, an enormous impact in the early history of the Uranian system could have broken the moon apart completely. Gravity then pulled the fragments back together, forming a patchwork world with mismatched blocks of terrain. The strange alignment of its coronae, the uneven distribution of craters, and the jumbled topography all support this possibility. If true, Miranda would stand as evidence that even small worlds can experience cataclysmic events and survive them. Both scenarios point to the same conclusion. Miranda was once geologically active. Beneath its icy crust may have existed pockets of liquid water mixed with ammonia, temporarily warmed by tidal or impact energy. As the moon cooled, those fluids froze again, locking fractures and ridges in place. The resulting surface preserves a record of motion, heat, and stress from billions of years ago. It is a snapshot of change frozen in mid-act, an unfinished story preserved by cold dot. The materials that make up Miranda reflect this complexity. Spectroscopic studies from Earth-based telescopes show that its surface is composed mainly of water ice, with traces of carbon compounds and possibly silicates. The bright patches visible in Voyager's images correspond to fresher, cleaner ice, while darker regions contain radiation-processed material. This mixture suggests that parts of Miranda have been resurfaced relatively recently, perhaps within the last few 100 million years. Wow. Others have remained unchanged since the solar system's youth. Miranda's small size makes its gravity extremely weak. A human standing on the surface would weigh less than 1% of their Earth weight. This low gravity affects how geological processes operate. Landslides and collapses that would spread widely on Earth instead form tall, sharp cliffs. Crater walls remain steep, and debris settles slowly. Combined with the deep cold temperatures average around 187 degrees Celsius, this means that geological features are preserved for eons without erosion. The moon's surface is a frozen archive of violence, unweathered by time. Scientists have also noted that Miranda's orbit lies very close to Uranus, only about 130,000 kilometers from the planet's center. This proximity means it moves through a strong gravitational field and within the fringes of the planet's magnetosphere. Charged particles from Uranus's magnetic field may periodically strike Miranda's surface, altering its chemistry. The constant bombardment could explain the moon's varying brightness and the faint blue hue seen in some spectral data, traces of radiation interacting with ice. Despite its quiet present state, Miranda may still experience subtle tidal forces. Even small variations in its orbit could generate minor internal flexing, enough to shift surface ice over time. If so, the moon's strange ridges and troughs might not be entirely static. They could still move, albeit at a pace far too slow for any spacecraft to witness directly. In this sense, Miranda remains a world in slow motion, frozen, but not entirely still. Future missions could reveal whether Miranda's complex features hide deeper secrets. High-resolution imaging might show whether the coronae are sites of ancient cryovolcanism, eruptions of slushy water and ammonia instead of molten rock. Radar and gravity measurements could determine whether residual liquid still exists beneath its surface. Such findings would have implications far beyond Uranus, shedding light on how small icy moons elsewhere might sustain temporary or recurring subsurface oceans, not among all the Uranian moons. Miranda stands as a reminder that size does not dictate complexity. A body barely 500 kilometers wide has produced terrain rivaling the drama of worlds thousands of times larger. Its fractures tell of heat and pressure, its cliffs of collapse and renewal. Even in the outer darkness of the solar system, where sunlight is weak and warmth rare, motion and transformation can still occur. Miranda embodies that paradox, a small, silent world that once moved with immense energy. Voyager 2's encounter with Miranda lasted only a few hours, but its images continue to shape how scientists think about planetary evolution. They showed that even distant frozen moons can record stories of catastrophic change. In the decades since, no spacecraft has returned to Uranus to study it further. Each new telescope image reminds scientists how much remains to be learned, and how many questions Miranda left unanswered. As we look outward from Miranda's scarred surface, another mystery comes into view. Encircling Uranus lies a delicate system of rings, thin, dark, and almost invisible. They form a quiet frame around the planet, shaped in part by the gravity of moons like Miranda. Their faint presence offers clues to the processes that sculpted the outer solar system. To understand that final layer of this distant world's architecture, we turn next to the faint rings of an invisible crown. For centuries, Uranus was known only as a pale point of light, its details hidden behind distance and darkness. When telescopes grew powerful enough to reveal its disk, astronomers imagined it as simple and featureless, a cold sphere drifting silently around the sun. But in 1977, a quiet discovery changed that perception forever. During a routine observation of a distant star, scientists saw the starlight flicker not once, but several times before and after Uranus passed in front of it. Those brief rhythmic dimmings revealed the existence of rings, thin bands of material encircling the planet like a delicate, invisible crown. Unlike the broad, brilliant rings of Saturn, Uranus's are narrow, dark, and understated. They reflect so little sunlight that even today they are almost impossible to see without special instruments. Voyager 2's flyby in 1986 confirmed their presence, photographing 11 main rings and hinting at several faint, diffuse bands beyond them. Since then, telescopes such as Hubble, and more recently, the James Webb Space Telescope, have detected 13 distinct rings, some dense and sharply defined, others faint and diffuse. Each ring lies within the planet's equatorial plane, tilted nearly sideways relative to the Sun, mirroring the strange geometry of Uranus itself. The main rings are astonishingly narrow. Most are only a few kilometers wide, confined by the gravitational pull of small moons known as shepherd satellites. These moons orbit just inside or outside each ring, their gravity maintaining sharp edges and preventing the material from spreading. The best-known examples are the moons Cordelia and Ophelia, which flank the bright Epsilon ring, the outermost and most prominent of the system. This ring is dense, composed of dark particles ranging in size from fine dust to small boulders. The inner rings, such as Delta, Gamma, and Eta, are thinner, still narrow, ribbons of debris tracing the invisible contours of Uranus's gravity field. What gives Uranus's rings their darkness is still a subject of study. Spectroscopic measurements suggest that the particles are coated with carbon-rich material, possibly produced by the radiation processing of methane ice. As charged particles from the magnetosphere strike the ring material, they may alter its chemistry, turning bright ice into darker compounds. This process, known as radiolytic darkening, gradually transforms the rings from reflective to nearly black over millions of years. The result is a system that absorbs most of the sunlight that reaches it, making it one of the darkest structures in the solar system. Darker even than coal dot, the faintness of the rings poses unique challenges for observation. Even powerful telescopes detect them only by the light they scatter at specific angles, or by the way they block background starlight. When viewed edge-on from Earth, the rings nearly vanish, their combined thickness measuring less than 100 meters. But as the planet's tilt changes through its 84-year orbit, the rings slowly open and close from our perspective. During equinox, sunlight strikes them edge-on, producing long, thin shadows across Uranus's atmosphere, fleeting moments when the planet's geometry reveals its delicate structure in sharp relief. The origin of Uranus's rings remains uncertain. Unlike Saturn's, which may have formed from icy material left over from the planet's formation, Uranus's rings appear younger and less massive. One possibility is that they are the remnants of shattered moons. Collisions between small satellites could have produced clouds of debris that spread into thin rings, before slowly settling into stable orbits. Repeated impacts with micrometeorites may have ground the fragments into fine particles, maintaining the rings over billions of years. Another possibility is that the rings are temporary, constantly replenished by material from the inner moons. As these small moons are struck by meteoroids, the impacts eject dust into space, which then joins the ring system before gradually falling back onto the planet. The interaction between rings and moons is dynamic and continuous. Gravitational resonances, where the orbital periods of moons and ring particles align in simple ratios, create waves and gaps in the rings, sculpting their patterns. In the epsilon ring, for example, tiny variations in density may be caused by the combined influence of multiple shepherd moons. The rings are not static bands, but living structures, shifting subtly under the push and pull of gravity. Over decades, scientists have detected changes in brightness and position, suggesting that these delicate bands breathe with the rhythm of Uranus's orbit. Voyager 2's images offered the first detailed glimpse of this hidden system. Against the darkness of space, the rings appeared as fine threads, faintly illuminated by scattered sunlight. Close inspection revealed that some rings were clumped, containing arcs or dense segments rather than being evenly distributed. These irregularities may arise from unseen moonlets, bodies only a few kilometers wide, embedded within the rings. Such moonlets act as gravitational anchors, confining material and shaping edges. Their discovery helped explain how narrow rings can remain stable for billions of years, despite constant perturbations from the planet and its moons. The temperature within Uranus's rings is extremely low, estimated at around -200 degrees Celsius. At such cold levels, the ices are brittle, and collisions between particles are gentle rather than violent. Over time, these collisions cause the particles to round and polish, producing smooth, dark surfaces. Radiation from the planet's magnetosphere continuously modifies them, creating an evolving balance between erosion and renewal. The rings are thus neither ancient nor new, but perpetually in transition, a quiet process of destruction and reformation that may continue indefinitely. In 2007, as Uranus reached equinox, the Hubble Space Telescope made an unexpected discovery: 2 additional outer rings far beyond the epsilon ring. These outer bands, much fainter and wider, likely contain finer dust particles. One appears blue, the other red, suggesting differences in particle size and composition. The blue ring seems to be maintained by the small moon Mab, which may act as a source of fresh material, constantly feeding the ring through micrometeorite impacts. This discovery expanded the known boundaries of the Uranian system and hinted that even more unseen structures may exist farther out, waiting to be detected by future missions dot from a physical perspective. The rings of Uranus provide valuable insight into how planetary systems evolve. They represent a middle ground between the dense, luminous rings of Saturn and the faint, diffuse debris belts around Jupiter and Neptune. By studying their composition and dynamics, scientists can trace the processes of accretion, fragmentation, and radiation that shape all planetary systems, from newborn disks around young stars to the remnants of moons around distant planets. Uranus's rings remind us that even minimal structures can reveal profound truths about balance and change. Despite their faintness, the rings exert a quiet influence on the Uranian system. They absorb sunlight, redistribute charged particles, and subtly affect the orbits of small moons. In return, the planet's magnetic field and radiation environment continually reshape them. This interplay of light, gravity, and magnetism creates a dynamic equilibrium, fragile but enduring. It is a balance that mirrors the planet itself, tilted, cold, yet sustained by intricate motion. In the coming decades, as the planet moves deeper into northern summer, sunlight will illuminate the rings from a new angle, revealing details unseen since Voyager's time. The James Webb Space Telescope has already captured images of the entire system glowing faintly in infrared light, offering a preview of what future missions might explore in detail. Each observation adds depth to our understanding of how these shadowy bands survive, change, and persist in the distant reaches of the solar system. The story of Uranus's rings is one of restraint, a quiet structure that hides in darkness, yet defines the character of the planet itself. They form the boundary between the world of Uranus and the vast emptiness beyond, linking moons, magnetosphere, and light into a single subtle system. But even beyond these rings, other mysteries wait. In particular, the question of what might lie beneath the icy surfaces of Uranus's moons. Could there be hidden oceans, still liquid in the cold, carrying the chemistry of life in silence? To explore this possibility, we turn next to oceans beneath the ice. When Voyager 2 left Uranus behind in 1986, it carried more questions than answers. Among them was one that continues to stir quiet curiosity. Could the planet's icy moons, frozen and seemingly lifeless, conceal oceans beneath their crusts? At first glance, such an idea seems unlikely. Temperatures in the Uranian system hover around -200 degrees Celsius, and sunlight there is only 1,000th as strong as on Earth. Yet time and again, planetary science has shown that warmth can exist in unexpected places. The same processes that heat the interiors of moons, like Europa or Enceladus around Jupiter and Saturn might, in gentler form, also operate here, far out in the cold. Uranus's 5 large moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are made primarily of water ice mixed with rock. This composition suggests that, when they formed, each moon held enough radioactive elements in its rocky portion to generate internal heat. Combined with periodic tidal flexing from Uranus's gravity, that warmth may have kept parts of their interiors liquid for long stretches of time. Even today, models suggest that several of these moons could retain subsurface oceans, sealed beneath dozens of kilometers of ice. They would be dark, isolated, and ancient reservoirs of liquid water persisting billions of years after their surfaces froze solid. Among the moons, Titania and Oberon are the best candidates. Both are large enough to have experienced significant heating after formation. Titania's vast network of canyons, visible in Voyager's photographs, points to a past of expansion, a sign that internal ice melted and refroze, forcing the crust to crack and stretch. Such fractures could mark the boundaries of ancient subsurface seas that once pressed outward against the surface. Oberon, though darker and older, may also contain a frozen ocean deep below, preserved by ammonia and salts that lower the freezing point of water. Even if these oceans no longer flow freely, they may survive as thick, slushy layers, remnants of a warmer past. Ariel, smaller but geologically younger, presents another mystery. Its surface is unusually bright and lightly cratered, with long valleys and smooth plains suggesting resurfacing within the last few 100 million years. Some researchers interpret these features as evidence of cryovolcanism, the eruption of water, mixed with ammonia through fractures in the crust. Such activity could have occurred if Ariel once harbored a subsurface ocean that occasionally broke through to the surface. Over time, those eruptions would have faded, leaving behind frozen channels and ridges, quiet echoes of liquid motion long gone. Umbriel, by contrast, seems inert and ancient. Its dark surface, heavily cratered and unchanged, shows little sign of internal activity. If it ever had an ocean, it likely froze early in its history. Still, models suggest that even a small fraction of residual heat could sustain a partially liquid core today. At temperatures near 176 K, ammonia-water mixtures can remain fluid, meaning that complete solidification may never have occurred. In planetary science, frozen often means only frozen for now. The possibility of hidden oceans around Uranus carries profound implications. Liquid water, even in darkness, provides a medium for chemical reactions, the foundation for what we call habitability. If these moons contain internal oceans enriched with ammonia, salts, and carbon compounds, they could host the same prebiotic chemistry thought to occur within the subsurface seas of Europa and Enceladus. No one expects complex ecosystems in such isolated worlds, but the simple chemistry of carbon, nitrogen, and hydrogen under pressure could create organic molecules, the first steps toward complexity. In this way, the distant moons of Uranus may extend the boundaries of where life-friendly environments can exist. Detecting these oceans, however, is a challenge. Unlike the active geysers of Enceladus or the magnetic signals of Europa, the Uranian moons reveal little from afar. Voyager 2's brief flyby provided only coarse measurements of their shapes and surfaces. To confirm the presence of liquid layers, scientists need more precise data, changes in the moon's gravitational fields, subtle shifts in rotation, or electromagnetic signatures that hint at conductive materials below. Such measurements can be made only by a dedicated orbiter, equipped with instruments to study both the planet and its satellites in detailed in preparation for future missions. Researchers are refining their models of how these oceans might survive. Computer simulations show that ammonia plays a crucial role. Even small amounts, as little as 5 to 10%, can lower the freezing point of water by tens of degrees. Salts, too, act as natural antifreeze, preventing total solidification. As a result, a moon that would otherwise freeze solid could retain a layer of viscous liquid between the rocky core and icy crust. That liquid layer, though perhaps only tens of kilometers thick, would affect the moon's density, magnetic properties, and surface features, clues that a future mission could detect. Recent observations from Earth-based telescopes and the James Webb Space Telescope have begun to refine our understanding of these moons. Infrared spectra show hints of ammonia hydrates and complex organics on their surfaces, materials that may have been transported upward from deeper layers. These detections strengthen the idea that the moons are chemically active, even if geologically dormant. Over eons, Cosmic rays and charged particles from Uranus's magnetosphere continuously modify surface ice, producing new molecules and slowly altering coloration. The chemistry of the surface, in this sense, may be a window into the chemistry below. If subsurface oceans exist, they raise another question. How long can they last? Over billions of years, radioactive decay diminishes, and tidal forces weaken as orbits stabilize. Without continuous heating, these oceans should eventually freeze. Yet some models suggest that conductive layers within the moons may trap heat effectively, slowing the cooling process to geological timescales. An ocean that formed shortly after Uranus itself may still linger today, cold, dense, and ancient, preserved beneath kilometers of unbroken ice. It would be a world within a world, silent, lightless, but not entirely still. Exploring such oceans would require new technology and patience. A future orbiter could measure the moon's gravity fields and magnetism to infer liquid layers, while radar instruments could probe beneath the surface ice. Even a single detection of a conductive, subsurface ocean would reshape how scientists think about the habitability of outer systems. If water and chemistry can coexist in a region as cold as Uranus, then oceans, and the potential for life's precursors, may be common throughout the galaxy. In planetary science, discoveries often begin with small, almost invisible clues. A bright patch on Ariel, a crack on Titania, a spectral line revealing ammonia. Each adds a thread to the larger tapestry of understanding. Together, they suggest that even in the faint outer reaches of sunlight, complexity endures. The oceans of Uranus's moons, if they exist, are not seas of motion and color, but of persistence, liquid maintained against time, heat preserved against cold. And so, the search continues. The next great step will not come from Earth, but from the spacecraft now being designed to return to Uranus, the first since Voyager 2's passing glance. That mission aims to descend through the atmosphere, orbit the planet, and map its moons in unprecedented detail. It may finally answer whether these hidden oceans are real, and if so, how they have endured for so long. To understand how such a mission will unfold, and what it could reveal about these distant worlds, we turn next to preparing to return, the Uranus Orbiter mission. Nearly 4 decades have passed since Voyager 2 gave humanity its only close look at Uranus. For all the insight that fleeting encounter brought, it left behind more mysteries than answers. What lies within the planet's icy depths? How do its tilted magnetism and extreme seasons shape its moons? And do the distant satellites still hide the ancient oceans hinted at by models and light spectra? To answer these questions, scientists have long dreamed of a return, a mission capable not of passing by, but of staying. That dream is now taking shape in the form of the Uranus Orbiter and Probe, a project that could redefine our understanding of the outer solar system. The mission is currently in its planning and design stages, under study by NASA's Jet Propulsion Laboratory and partner institutions. It was identified as the top priority for flagship exploration in the U.S. National Academy's Planetary Science and Astrobiology Decadal Survey, published in 2022. Report placed Uranus above all other targets for the coming decades, describing it as one of the most important and least explored worlds in our planetary system. This recognition marked a turning point, a quiet acknowledgement that the calm blue planet, long overlooked, has become a key to unlocking the history of planetary formation. The proposed Uranus Orbiter and Probe mission would be an ambitious, long-duration exploration. Its design follows a principle of endurance, a spacecraft built to travel more than 3 billion kilometers, survive for decades, and study an entire planetary system. If launched in the early 2030s, it could arrive in the mid-2040s, reaching Uranus near its northern summer, a time when the planet's rings, atmosphere, and moons will be fully illuminated by sunlight. This timing would allow direct comparisons with Voyager's data, gathered during the southern summer nearly 60 years earlier, revealing how the planet's seasons evolve over an entire Uranian half-year. The mission is divided into two main components: an orbiter to study the system from above, and a probe to descend into the atmosphere. The orbiter would enter a long looping orbit around Uranus, spending years observing its weather, magnetic field, and moons. It would carry cameras, spectrometers, magnetometers, and particle detectors, instruments designed to sense everything from cloud patterns to charged particles in the magnetosphere. The atmospheric probe, released during the spacecraft's arrival, would plunge into the planet's upper layers, measuring temperature, pressure, composition, and wind speed before being crushed by the rising density. Together, these two components would provide the first comprehensive view of Uranus, from its icy exosphere to its hidden heart. One of the mission's most important goals is to understand how ice giants form and evolve. Uranus and Neptune occupy a category distinct from gas giants like Jupiter and Saturn. Their masses, compositions, and internal structures represent an intermediate step, a class of planets made mostly of water, ammonia, and methane rather than hydrogen and helium. By studying Uranus, scientists hope to learn how common this type of planet may be in other star systems. Observations from telescopes such as Kepler and TESS have shown that planets similar in size to Uranus are among the most frequent in the galaxy. In that sense, studying this pale blue world is also a way of studying countless others. The magnetosphere of Uranus will be another focus. Voyager 2 revealed a field unlike any other, tilted, off-center, and constantly shifting. The orbiter's magnetometer will map this field over time, tracing its motion through the planet's long seasons. By correlating magnetic measurements with changes in the atmosphere and auroras, scientists can model the structure of the conducting layer inside, a step toward solving the mystery of the planet's asymmetric dynamo. These insights could explain why Uranus emits so little internal heat and how its internal architecture differs from Neptune's. In turn, that knowledge will help refine theories about how all planets cool and evolve over billions of years. The orbiter will also study Uranus's rings and moons in detail. High-resolution cameras will capture the fine structure of the rings, detecting embedded moonlets and measuring particle composition. Spectrometers will identify the chemical signatures of carbon compounds and radiation-altered ice, shedding light on how these dark rings persist over time. The orbiter's instruments will map the surfaces of Titania, Oberon, Ariel, Umbriel, and Miranda in resolutions far surpassing Voyager's grainy images. Gravity and radar measurements could reveal whether any of these moons harbor subsurface oceans, the quiet, dark seas hinted at by their fractured crusts and reflective ices. If confirmed, it would extend the known boundaries of potential habitability to the cold reaches of the solar system's edge. The atmospheric probe, though small, will play a crucial role. Descending for less than an hour through Uranus's upper atmosphere, it will send back data in real time via the orbiter before being destroyed by pressure and heat. Its sensors will measure concentrations of hydrogen, helium, methane, and trace gases such as ammonia and hydrogen sulfide, the ingredients that give Uranus its distinctive blue color. It will also record wind speeds and turbulence, providing a direct profile of atmospheric motion. This data will allow scientists to test whether the planet's unusual coldness is caused by layering, chemical composition, or a loss of internal heat long ago. It will be a short descent, but one that could redefine decades of planetary models. Designing such a mission poses immense technical challenges. Because Uranus lies nearly 3 billion kilometers from the Sun, solar power is impractical. The spacecraft will rely on radioisotope thermoelectric generators, RTGs, nuclear batteries that convert heat from decaying plutonium into electricity. These have powered all previous deep space missions, from Voyager to New Horizons, and are among the most reliable technologies ever built for space exploration. Communications, too, will require patience. A radio signal from Uranus takes nearly 3 hours to reach Earth, meaning commands must be planned days in advance, and every piece of data will arrive with a time delay. Even at the speed of light, exploration here happens slowly. Despite those difficulties, the scientific rewards are immense. A Uranus orbiter would provide insights into planetary formation, magnetic dynamos, atmospheric chemistry, and the evolution of icy moons, fields that link directly to the study of exoplanets and the origins of life. Its discoveries would bridge the gap between the inner solar system, now well explored, and the distant frontier of Neptune and beyond. In a sense, it would complete a journey that began nearly half a century ago with the Voyager missions, the continuation of humanity's slow, deliberate expansion into the deep outer dark. Planning such a mission also involves patience on a human scale. If launched in the early 2030s, the spacecraft would not arrive until many of its builders and planners are retired. It will be tended by a new generation of scientists who grew up studying the data from Voyager and dreaming of this return. Space exploration, especially at this distance, is a collaboration across time, one that demands endurance not only from machines, but from people. It is a reminder that knowledge itself often unfolds at a slower pace than a single lifetime. NASA and the scientific community hope that this mission, once approved and funded, will be launched by an Atlas V or Falcon Heavy rocket, with an assist from Jupiter's gravity to shorten the journey. Once there, the spacecraft would spend at least 5 years in orbit, mapping, measuring, and observing. It would watch the changing cloud bands, track storms, study auroras, and document the dance of moons around their tilted planet. Every observation would add to a record meant to last, a comprehensive atlas of Uranus and its system in the calm rhythm of exploration. The Uranus orbiter and probe mission stands as the next logical step, not a race for discovery, but an act of continuity. It builds on the legacy of Voyager and Cassini, carrying forward the quiet persistence that defines planetary science. Each decade adds a new piece to the vast mosaic of understanding, and this mission promises to fill one of its most significant gaps. It reminds us that even at the edge of sunlight, curiosity endures, a light that travels farther than any spacecraft. When it finally departs from Earth and begins its long journey outward, the spacecraft will cross a gulf so wide that sunlight becomes a whisper. It will glide for years through the silent expanse between worlds, following a path once traced by Voyager toward the faint blue point that has waited patiently for its return. And when it arrives, it will not merely revisit an old mystery. It will open a new chapter in how we see the architecture of the solar system itself. For that is the purpose of this journey, to turn brief glimpses into lasting understanding, to see Uranus not as a quiet outlier, but as a central key to the story of planets, how they form, change, and survive. And as we prepare for this next voyage, we also prepare to reflect on what these decades of exploration have revealed about us and our place within the greater whole. That reflection becomes the quiet closing thought of this exploration, the final chapter, a quiet revolution in understanding our solar system. In the story of exploration, Uranus has often stood apart, not because it is the most distant or the most mysterious, but because it quietly resists comparison. It is a world that does not fit easily into patterns, a planet that challenges every neat category astronomy has tried to impose. For centuries, it waited in the outer dark, slowly turning on its side, until human eyes and instruments were finally able to reach it. And now, after decades of reflection, scientists are beginning to realize that this strange, calm planet has quietly revolutionized how we understand the solar system itself. When Uranus was first discovered by William Herschel in 1781, it doubled the known size of the solar system overnight. At that moment, the universe became larger. What had once seemed complete, the familiar dance of 6 planets, suddenly expanded, revealing that the cosmic order was not finished, but open-ended. That discovery was not only about a single planet. It was a shift in thought, a recognition that there was still more to find beyond the horizon. In many ways, that same awareness continues today, shaped by the questions Uranus still poses. Over the last 2 centuries, each new observation of Uranus has altered the framework of planetary science. Its tilted rotation defied conventional models of planetary formation, suggesting that collisions and chaos play as much a role in creation as order and symmetry do. Its magnetic field, skewed and displaced, showed that dynamos, the internal engines of magnetism, can behave in ways previously unimagined. Its rings and moons, faint and complex, revealed that even in the outer reaches, gravity maintains delicate balance through unseen forces. And its cold, muted atmosphere challenged long-standing theories about how heat, energy, and chemistry interact inside giant planets. Every discovery about Uranus seems to whisper the same message, that the solar system is not simple, but subtle. The insights drawn from this distant world have also changed how we look outward, beyond the sun, into the galaxy. The thousands of exoplanets discovered over the last 3 decades include many that resemble Uranus in mass and composition. They are often described as mini-Neptunes or ice giants, worlds wrapped in clouds of methane and water vapor, orbiting stars at distances where sunlight is weak. By studying Uranus, scientists gain a living reference point, a way to interpret what telescopes detect light years away. The physics that governs its storms, magnetism, and internal structure may be echoed across countless other systems, each shaped by the same universal laws. In this sense, Uranus connects the intimate scale of our solar system with the vast architecture of the cosmos. It shows that the processes shaping planets here are not unique, but common, recurring patterns written into the physics of matter and motion. From the turbulence of its upper atmosphere to the quiet density of its core, Uranus reflects the balance between energy and stillness that defines planetary life. It is a reminder that the universe is not built of isolated wonders, but of repeating themes, variation within order, difference within harmony. There is also a deeper, quieter meaning in the story of Uranus's exploration. For more than 40 years, humanity's only direct view of the planet has come from a single spacecraft, Voyager 2, that passed by for just a few days. All that we know, the temperature, the winds, the moons, the magnetic field, stems from that brief encounter. And yet, those few days have sustained generations of inquiry. They have inspired simulations, research, and entire missions still in design. From a single point of contact, an entire field of knowledge has grown. It is a quiet proof that even fleeting moments of discovery can echo for decades as we prepare to return. Through the planned Uranus orbiter and probe mission, we carry not only instruments but memory, the record of how our understanding has matured. When Voyager flew past, planetary science was still in its youth. Each new image, each signal from deep space was an introduction. Now we approach with more questions, but also more patience. We know that discovery is not a flash of revelation, but a slow unfolding, a dialogue between what we see and what we understand. The mission to Uranus will continue that conversation, deepening rather than completing it. Perhaps what Uranus teaches best is humility. It shows how easily our assumptions about simplicity can be overturned. A world once thought static reveals storms with winds faster than hurricanes on Earth. A planet that emits almost no internal heat still hosts intricate weather patterns. Moons that seem dead may conceal oceans beneath their crusts. Every observation opens new complexity, showing that silence does not mean absence. That calm can hide immense depth. This quiet revolution in understanding is not only about Uranus. It is about the nature of exploration itself. In a time when technology moves quickly, Uranus reminds us that the universe unfolds on its own timescale, measured not in days or years, but in orbits and eons. Its 84-year journey around the Sun is a reminder of endurance, of how change and repetition coexist in cosmic rhythm. Each season on Uranus lasts more than 2 decades, teaching patience, a kind of cosmic stillness that science must learn to match. Knowledge, like light in the outer solar system, travels far and slow. The renewed interest in Uranus also marks a turning point in the story of the outer planets. Jupiter and Saturn have been revisited many times. Neptune, too, waits its turn. But Uranus sits between them, both literally and conceptually, a bridge between gas giants and ice giants, between known and unknown. It is a transitional world, and perhaps that is why it feels so essential to study now. In its intermediate nature lies a key to understanding how planetary systems form, not as isolated extremes, but as gradients of energy and matter. When the next spacecraft finally arrives, decades from now, it will see a different Uranus than Voyager did. The sunlight will fall from a new angle. The rings will cast different shadows. The poles will face the sun in reverse. But the deeper mystery will remain the same: how a planet so far from heat and light can sustain such complexity. That question will guide new generations of scientists. Linking curiosity across time, and as we look further, to the worlds beyond Uranus, Neptune, Pluto, and the Kuiper Belt, the lessons learned here will guide exploration outward. The same methods, the same patience, the same quiet science will continue to unfold, step by careful step. In this way, Uranus becomes not the end of a journey, but a beginning, a reference point for what lies beyond. Both in the outer solar system and among distant stars. In the calm of that thought, there is perspective. Every mission, every observation is part of a long continuum. The faint light reflected from Uranus today began its journey hours ago. The data we receive comes from years of travel. The understanding it brings will echo for generations. Knowledge, like orbit itself, is circular, returning again and again, each time a little deeper, a little clearer. And so this exploration closes not with a conclusion, but with continuity. Uranus remains there, in the far reaches, turning slowly beneath its tilted sky. The rings still shimmer faintly in scattered light. The moons still circle in their ancient rhythm. The magnetic field still dances at odd angles through the planet's night. The story is not finished. It is simply ongoing, waiting for the next observation, the next spacecraft, the next mind willing to listen to what this quiet world has to say. Perhaps that is the real revolution Uranus offers. Not the discovery of something new, but the rediscovery of how to look, patiently, attentively, and without haste. In its stillness, the planet invites a different kind of understanding, one that values depth over speed and questions over certainty. It teaches us that in the calm, there is movement. In silence, there is meaning. And in the most distant places, there is always something left to learn. And as we end this long journey through the distant blue, it is clear that Uranus is not merely a planet at the edge of sunlight. It is a mirror reflecting the quiet persistence of curiosity itself. In that reflection, science finds what it has always sought, not final answers, but enduring wonder. Thank you for sharing this calm journey through the distant blue. If you found peace or wonder in this quiet exploration, you can like, subscribe, or leave a thought below, gently in your own time. There are more worlds waiting, softly turning in the dark, and together we'll visit them soon. Until then, sleep well, stay curious, and remember, you're always welcome here at Calm Science Sleep.